Welcome back to ECE 501B. Your project is due today, and hopefully you've either submitted that via the Dropbox, or you will, or you'll hand in a hard copy either in my physical mailbox or at the front of the classroom by the end of the class period. Today, oh, final exam review session. Yes or no? Do you want me to try to send out some times and I'll put that on a quiz in D2L and you can vote? But it may be Thursday or Friday. That's about the only days that I think it could possibly work. And it may be that it happens on that reading day, which is Thursday. I don't know. We'll see. So I'll try to suggest sometimes. I already have one scheduled for another class, but we'll see if that can be done. Your final exam is a week and 2 hours from today, or from right now. It's at 6 o'clock on Monday, the 16th of December. Hopefully that's not a surprise to anyone. And you have 2 hours more to prepare instead of normally when you come into class at 4. So hopefully I will see all of you for the final exam on that Monday. Today we are getting into the second half of the class now that we have 2 lectures left. Actually, it's the textbook on functional analysis that's really a subset of functional analysis. The title of the book is Signal Theory. You have access to that book courtesy of the author through the D2L website, and you should be starting to read that. We'll go through a motivational example, which is really convolution as a linear operator. And what does that mean? We can view convolution as if it's now producing eigenfunctions and eigenvalues. And what are these eigenvalues? And we'll see that that's actually the transfer function, which is now a continuously varying function of omega and not some finite dimensional index I. But that's how we will motivate this new idea of, instead of dealing with vectors, now we're dealing with signals, and we'll make sets out of signals. We'll talk about particular examples of sets of signals, and then we'll say, well, how can we use that? And you might be thinking, Frank's is coming from a communications perspective in terms of the book and the underlying ideas and examples, but you might think of ones and zeros, and if you now transmit a 1 or a 0, that signal will look different, and hopefully when it goes through the channel and you measure it, you'll be able to capture it as what it was intended to be, a 1 or a 0. And Franks was teaching classes at Bell Labs. That was back in the rewrite or the revised version of this, I think, was 1981, and that was when Bell Labs was still existing and in its older form, and there was a lot of communication information being dealt with at that particular time. Then we will get into set partitions and equivalences, or equivalence classes or equivalence sets. How do we collect? Maybe we break up this signal set into 2 partitions. One partition says, oh, that was a 1 that was transmitted. Another was, oh, that was a 0 that was transmitted. And that now splits this signal set into 2 places, and now we simply need to figure out, how do we decide which place we are at? Was it a 1 or a 0 that was happening? Let's then get started. And first, you won't have to intimately absorb all 10 chapters of Frank's before next week, Monday at this time, but I will tell you a little bit about what it is now, and then we'll get into the first couple of chapters of Frank's in today and Wednesday. And I think you'll be hopefully pleasantly surprised that the concepts and the ideas that you've now learned in a finite dimensional setting carry over into an infinite dimensional setting, and you can now start to conceptualize these ideas in a way consistent with what you've already learned, and it won't take you as much to get up to speed, and you can more easily or more smoothly read the material in this textbook entitled Signal Theory by Franks. As I said before, it's a subset of functional analysis, meaning if you wanted to get even more expansive, you would be studying the set of topics in functional analysis. We're going to be specializing that to the material in Franks, which is signal theory, and in particular, he talks about if we are dealing with signals, usually those signals are carrying some kind of information. And if you thought of a digital communications course, you would be thinking ones and zeros. We're trying to now figure out what's a 1 and what's a 0, and how do we distinguish between those. Or we might be interested then, if we're dealing with signals, how are these signals classified? In earlier classes, maybe you classified signals as energy or power signals, and that hopefully then has some meaning to you. Is it a finite energy signal? Is it a finite power signal? And obviously power signals would have an infinite amount of energy if you were looking at that, so there is a distinction between energy and power. And not only do we worry about how signals can be classified, but we also want to understand how we are going to represent those. So how are signals classified and represented? In the textbook of signal theory, Franks takes this signal space viewpoint. And from that, it provides actually a geometrical view of signals, just like we've talked about vectors and how that sort of gives us this in 3 space, maybe a geometrical insight into n-dimensional vectors. Now we have this geometrical view of signals and signal processing operations. How can we then manipulate those signals with operations to produce the results that we want? Maybe that will enhance our ability to determine whether or not something is a 1 or a 0. Again, I'm going back to that basic idea. But in the book, you can think of the book being separated into 2 parts. The first 5 chapters represent the foundational material. And again, that should parallel or be consistent with the first or the material that we've already covered in the finite dimensional textbook by Axler. And you'll see this consistency or the same kind of ideas. Then the last 5 chapters are producing applications. And what we want to do is hopefully make this transition between the 2 textbooks smooth and more expedient in terms of getting into the functional analysis or the signal theory based on what we've already done this semester. Our previous material in the Axler text dealt with finite dimensional spaces, r to the n or c to the n. Now what we want to do is extend that idea or those concepts to infinite dimensional problems or systems or signals. Let's look then at a general introduction to this. and motivation. Suppose we look at the following list form. Maybe I give you a list X that looks like X sub 1, X sub 2, on up to X sub n, and those were coordinates in what we've already looked at. And now let's plot those, though, those coordinates, as if each coordinate was maybe a time index. So that now, in this case, let's say that n is equal to 8, and we're going to be plotting X sub I for the I up to 8. Whoops. First you have to learn how to count. But now we might have 8 different values. Each value now is representing a coordinate in that list, X sub 1 through X sub 8 in this case. And that may fluctuate. It may be positive, it may have some negative values. If we now start to zoom out on this and we increase the number of values in our list to 16 and we still plot X sub I, now maybe what we have and I should have kept those all the same length. So now subdivide your 8 into equal pieces and you get 16 points. I went too far. I guess I didn't do it too far out, so I can actually redo mine to where now I have 16, and these are supposed to be 1, 2, 3. Those are closer, more densely packed, and now we might have the same kind of pattern appearing as we zoom out. I didn't put 16 dots there because I didn't think I was getting very consistent with my earlier dots of 8, but you might then have sort of this same behavior as you zoom out with n equal 8. Now, as we let n go to infinity, that's where we're going to be heading now. As n goes to infinity, and let's say, and we keep zooming out, then x starts to look like a function. Meaning now maybe we have time that's continuous, and we might have now something that looks more like that. And this is now x of t, where here we're letting n march off to infinity as we zoom out even more. These discrete coordinates now become this continuous variable time, let's say t, and x sub I now transitions into x of t. Where now instead of a finite dimensional space, we now have an infinite dimensional vector. And a lot of times when that's the case, we may actually refer to it or call it something different. Now it might be called, instead of a vector space, now maybe we'll call it a signal space, since maybe that's what it is a signal. Or you might hear it called a function space. if we utilize the same kinds of notions that we've done before, we can actually make those signal spaces or function spaces linear if we give them the appropriate addition and scalar multiplication properties that we've done before to make something linear. So it's linear with the standard, let's say, definitions of addition and scalar multiplication. With those underlying, so now we have a signal space, and we may now allow for linear operations on these signals to give us maybe operators so that we can now map between signal spaces like we've done between vector spaces. Many of the results that we've had from the finite dimensional case apply directly to this new setting of signal space. Let's look at a motivational example to see where that might be. And what we want to do now is think of linear operators. Operators we were mapping from one space back to itself, the same space. And on those, or with respect to linear operators, we have defined eigenvectors with those linear operators. We also have been able to parameterize a vector in terms of maybe these eigenvectors, so that we now have a way of describing or representing a generic vector as a linear combination of these eigenvectors, these alphas or a's as far as the weighting. So we have a vector representation or vector representations in terms of these eigenvectors. Now, as sort of a review, we can remind ourselves of as to what we have with respect to the eigenvalue-eigenvector equation. We have this t, a linear operator, operating on a vector, v sub I. If v sub I is an eigenvector, then the operator really just expands or contracts in that one direction, v sub I, with respect to our eigenvector. What we want to do is generalize that to this new concept of eigenfunctions. Now consider what this would look like for eigenfunctions. For example, suppose now that I have t. That's now still a linear operator, but now I'm going to say, oh, v sub I of t is going to be the ith eigenfunction. Lambda sub I is going to be the ith eigenvalue that then operates on v sub I of t. Here is now our linear operator. V sub I is now our ith eigenfunction, and lambda sub I is the ith eigenvalue. And to sort of get a better feel for what we're doing here with respect to this linear operator t on an eigenfunction mapping into some linear scaling or some scalar multiplication of that eigenfunction, let's look at an example that we're used to, or what I'm assuming we're used to, and if you're taking my other class, you better be familiar with it for the final exam, and that's convolution. So now let's consider an operator that we're hopefully somewhat familiar with. Consider an operator you're already familiar with. In particular, let's assume that we have an LTI system, a linear time invariant system. And I'll just go ahead and not even surprise you with what it is. I'm going to just say it's convolution. And do you remember the expression for that? Y of t. The output is now some integral, potentially from minus infinity up to positive infinity, of x of t minus tau, h of tau, d tau, where x is, let's say, our input signal, h is the impulse response of the system, the linear time invariant system that we're passing that or applying that input signal to, and out pops the output, y of t. We could simply say, well, that's t, a linear operator operating on this input x of t. Pictorially, we have our system h of t in between our input x of t and our output y of t. And typically, in this picture, x and y are living in the same space of waveforms. So this is then a linear operator, t is, since we're taking x of t into y of t, where x and y are the same space. It's an operator because both x of t and y of t are in the same space. Now, for a linear time invariant system and that integral relationship, which we know is convolution, our claim is that e to the I omega t is actually going to be an eigenfunction of this linear operator t. Let's check that. So if e to the I omega t, this complex exponential, is an eigenfunction of this linear operator t, why don't we let our input just be that e to the I omega t? If that's the case, and now we apply that or use that in our integral relationship, y of t now becomes this integral from minus infinity to infinity over tau. That's now equal to x of t minus tau. So if we go if x is now e to the I omega, we now simply say, oh, this is t minus tau. This is now h of tau d tau. And now we simply use the relationship that we know, or the properties that we know are true for exponents. We have really this product of two pieces that are exponential, which we've basically abbreviated by combining them in the exponent with just this subtraction or this addition. But we can pull that apart. We have an e to the I omega t and an e to the minus I omega t, or tau. Well, the tau piece needs to stay inside the integral, but the t piece can come outside the integral because it's not a function of our variable of integration. If we do that, we can now rewrite this and say, okay, this is now an integral from tau equal minus infinity to infinity of e to the minus I omega tau, h of tau d tau, and outside of that is what's left over, which is e to the I omega t. But this is what we called our eigenfunction. This is our eigenfunction, and now what's happening to that is really just a scalar operating on that eigenfunction. Now the scalar might be complex, but that's okay. Which now, if we view this as this t of x of t, now maybe you can see that t of e to the I omega t is now just some lambda. Let's subscript it now with an omega, not a lambda sub I. Our variable now is omega, and it's a continuous parameter, not a discrete labeling of our scalars. That's now times e to the I omega t. So we injected this eigenfunction into our system, and out popped something in the same direction, in the same space, just scaled by this scalar lambda of omega, or lambda sub omega. Now that I've already scrolled it off the screen, what is our lambda sub omega? It's just what's in the square brackets. So that now if we say, oh, lambda sub of omega is now this integral from minus infinity to infinity of e to the minus I omega tau, h of tau, d tau. But maybe you recognize that as the Fourier transform of this impulse function h of tau, or h of t. And we can now call that capital H of omega. And that's now consistent with this eigenvalue, lambda of omega, that we're used to seeing when we had this linear operator t. Meaning now we can think of this linear operator t operating on this eigenfunction e of I omega t is now simply h of omega, the eigenvalue, times the eigenfunction e to the I omega t. Where now what we have to remember is what we've done. We were indexing everything with this finite index, I, 1, 2, up to 8, 1, 2, 3, up to 16. Then we let it go to infinity, and now that index became continuous. By moving to the continuous setting, that caused the indices to become continuous as well. So that lambda of omega, or that capital H of omega, now are continuous functions of our index omega. These eigenfunctions are now indexed by this continuous parameter omega. And we could, we could re-sketch that. We now have this LTI, this linear time invariant system. We have our eigenfunction V indexed with omega, which was now this just e to the I omega t. And when I have that complex exponential in earlier classes at the undergraduate level, I just say, think of sines and cosines when you see e to the I omega t. That's a complex phasor, but really combinations of those are just sines and cosines at a particular frequency omega, but now we're letting that frequency be any variable omega that we want it to be. We then apply that to this linear time invariant system, and out pops for an output a scaled version of that same eigenfunction, where the scaling now is this transfer function h of omega that you've maybe had in earlier classes. If we now said how many of these eigenfunctions are there, for this infinite dimensional operator, how many eigenfunctions are there? We have one structure, don't we, e to the I omega t, but that represents an infinite number of eigenfunctions because we're letting omega be this continuous variable. So it is one structure, e to the I omega t, but that actually represents an infinite number of eigenfunctions because omega can assume any parameter value on this continuum. So there's our infinite dimensional space, which we will get into in a minute, but that's now this function space. So we can interpret this capital H of omega, this transfer function, H of omega, as the eigenvalue spectrum of our linear operator T, our infinite dimensional operator T. So that now you sort of have a different perspective on this transfer function. Now if somebody says, what's h of 3? You go, oh, that's like the eigenvalue. That's how that system amplifies or attenuates frequencies at 3 radians per second. That's like my eigenvalue at that particular frequency, and that's the transfer function h of omega. Let's now that we sort of have this idea in terms of eigenfunctions, let's see about writing any generic signal in terms of these eigenfunctions. Meaning, now let's recall the importance of the eigenvector decomposition for analyzing operators on finite dimensional vector spaces. Meaning, remember where we had just a generic vector v, that was now some sum over this index I of, let's say we had an n-dimensional vector space. We would find the eigenvectors of some operator, and now we would rewrite or represent any generic vector in terms of those eigenvectors, E sub I. And if the operator has special properties, if it's self-adjoint, if it's normal, etc., then we have the possibility of having orthonormal eigenvectors, and that makes this parameterization even cleaner. But now this is some arbitrary vector v that we're just writing or written in terms of the eigenvector basis. Well, don't need multiple or plurals. That's just one set of basis vectors. If we now have any vector v written this way, what happens, or now remember, so we're sort of reviewing a little bit, what happens when we have that operator applied to that vector v? Meaning now we have t times this sum of a sub I, e sub i's. But if the e sub i's are eigenvectors, what happens when we have t operating on an eigenvector? The a's are scalars. Those just, we can factor those out, and now we have a sum of a sub I, t e sub i's. But t e sub I, if those are eigenvectors, are just scalar multiples of e sub I, which we've called the eigenvalues, lambda, as the scalar. So that now this is simply this sum of a sub I, lambda sub I, e sub I. And that's actually a very simple process in terms of how that operator processes any generic signal or vector v. So this is a very simple process that results from using eigenvectors as the basis. Now, in representing v, how did we get those a sub i's in the first place? If we have a generic vector v and we want to know how do we parameterize that or represent that or write that as a linear combination of our eigenvectors, how did we find the a's, the a sub i's? Inner product or a projection, right? So that was just a projection. We just projected the vector v onto each of these eigenvectors e and figured out how big of a component of v aligned with each of these eigenvectors, e1 through e sub n. Pardon? This is not, well, this is, so what we're doing now, I guess, yes, so the question was, this is only true for orthonormal. if we want to collapse it down, we could have generalized this to where the eigenvectors were not orthonormal, and then we would have multiple projections. So let's just view it in the simplest case where we do have the eigenvectors being orthonormal, and that's what I'm going to say here. So now if we do that, now we have this projection of A sub I is equal to this inner product of V with the respective E sub I. So let's just say the E sub j's are orthonormal, just to make it easier. We would have components in different places if we didn't have our eigenvectors all orthogonal to one another. But we would still have pieces of those. Now, what happens if we apply that same idea in the infinite dimensional case? Or what happens in the continuous case? If we go back, I guess we haven't done it yet, but now we want to find how to parameterize any vector as some combination of these eigenfunctions. Meaning, if we said, oh, let's say we now have an A of W, where W could be this continuous parameter, it's not just a discrete index. If we do the same thing, we would say, oh, X, now for just a generic waveform, we want to take the inner product of that with each of these eigenfunctions, V sub omega. Or this now says X of t, we want to inner product with e to the I omega t. Let's just remind ourselves what we might want to produce or use as an inner product. If we had two waveforms, A of t and B of t, that are functions of time, then we could define an inner product as this integral from minus infinity to infinity of A of t and the complex conjugate of B dt. If we use that inner product, A of omega or A sub omega now is this integral from minus infinity to infinity of x of t, and now we want to weight that by the complex conjugate of our eigenfunction v sub omega. Now we simply take the conjugate of e to the I omega t. But that's simply e to the minus I omega t dt. And that should look very familiar. That's now the Fourier transform of x with respect to these multiple or this infinite number of eigenfunctions if they were parameterized by this variable omega. Now x of t can be written in terms of those coefficients or those scalars, those a of omegas. And x of t can be written as weighted sums of these v of omegas. Meaning x of t now, if we were in the earlier part of the class, this would be this finite sum of the a sub i's, e sub i's. But now the e sub i's are the v sub w's. We no longer have a finite number of them. We have an infinite number, so now we have to integrate instead of sum. And the a's are now this made up of these integrals. So that now we could say, we can write x of t as this sum from minus infinity to infinity of the coefficients, or these scalars, a of omega, e to the I omega t, that's the v of omega, d of omega. And this is an integral because now we're dealing with this continuous parameterization by omega. And now what was x of omega, capital X of omega? That was just the little a of omega. Think of this in terms of what we had before, where we might have had x of t was equal to this sum of a sub I, e sub I. That's what we're sort of redoing in the continuous setting. So this was in our finite dimensional case. And really we were not using x, I think we were using v back then. But so we had this v, and maybe we didn't have it parameterized by t, so now we just had this v that's equal to this finite sum of eigenvectors. Now we have the sum becoming an integral. The coefficients now are continuous. That's why we had to switch from a finite sum to an integral. And our eigenfunctions now are replacing the eigenvectors. And this now looks like a representation of a general waveform or signal x of t, like a generic vector v is represented in terms of the eigenvectors. What is capital we could refer to capital X of omega as a of omega, which is just this integral from minus infinity to infinity of x of t. That's what we just found right there, the a of omega. That's now x of t e to the minus I omega t dt. And these a of omegas actually represent, or are, you could think of as coefficients of the signal x in the frequency basis. So the a of omega represent the coefficients of signal x of t in the frequency basis, in the omega basis. Or you could think of x of t now as the same underlying signal. It's just now x of t represents the coefficients of the signal x in the time basis. Meaning you can now think of that underlying signal x either in the time domain, giving you an x of t, or you could think of it in the frequency domain by means of its coefficients or its components in certain frequencies, the a of omega. If we now use all of this in our initial convolution integral, what does that produce? Y of t was this integral from minus infinity to infinity of x of t minus tau, h of tau, d tau. That now actually, if we, and maybe I'll go ahead and derive that because maybe it's not completely clear, but that's now the same as taking y of omega and inverse transforming. But we will show that that's equivalent to the frequency representation of x, the frequency representation of our transfer function, and then weighting that by this e to the I omega t. That's now how, what? Capital Y of omega would be the coefficients of e to the I omega t, or this expansion of y of t in the frequency space. So that this now is where we get this concept that always seems to be expressed to you. Convolution in the time domain is going to produce or lead to multiplication in the frequency domain. Remember, over here, this is because e to the I omega t is an eigenfunction. So that this piece is the frequency domain, or the frequency space representation or coefficients of y of t. Do you want to derive that or see where that comes from? We have y of t is this integral from minus infinity to infinity of x of t minus tau, h of tau, d tau. That's the convolution integral where we are integrating with respect to this variable of integration tau. But that's equal to, why don't we replace h of t with its representation in the frequency domain? Meaning we could rewrite little h of tau as this integral from omega equal to minus infinity to up to infinity of h omega. Those are its weighting coefficients. E to the I omega, well, let me do tau. D omega d tau. And let me just go ahead and play sort of fast and loose with the order of the integration. Let me pull that omega out of everything. So now we're integrating from omega equal to from a minus infinity to infinity, integrating with respect to tau from minus infinity to infinity. We have x of t minus tau, h of omega, e to the I omega tau, d tau, d omega. Haven't really changed anything, just sort of relocated some of these expressions, pulled the integration outside of everything. But to simplify this, why don't we, or to play with this a little bit more, let's consolidate that argument of our input signal x. Let's redefine that argument to be just one variable sigma. So let's let sigma equal t minus tau, and then d sigma, in terms of tau, we're going to assume t is constant, is minus d tau. And if we wanted to replace tau anywhere in our expression, if we solved for that, that's now t minus sigma. If we use that variable substitution, y of t is now this integral, omega equal minus infinity to infinity. Sigma now goes from infinity to minus infinity, since we've changed the sign on sigma and tau through that variable substitution. We now have x of sigma, h of omega, e to the I omega, but now we replace tau with t minus sigma, minus d sigma d omega. And we can absorb that minus sign by reversing the order of integration, or the integration with respect to sigma, and now we have this integration omega equal minus infinity to infinity. We have sigma going from minus infinity to infinity. We now have x of sigma. Let's now pull apart that complex exponential and put the sigma with respect, or close to the x. We now have e to the minus I omega sigma d sigma. H is only a function of omega, and we have e to the I omega t d omega, and we can actually now see that hopefully that term in the blue bracket is the way of finding those coefficients in the omega domain, which is capital X of omega. So that now we have this integral from omega equal minus infinity to infinity of capital X of omega, h of omega, e to the I omega t d omega. And that's the end of our derivation for that. But we can hopefully sort of see that now y of omega, these coefficients for the representation of y of t in the omega space, is made up of the product of these transforms, h and x. What's that saying? Now, all of that Fourier stuff that you ever learned, you can think of in terms of what we've now studied in terms of eigenvalues and eigenvectors. So all of this Fourier analysis and am I so bold as to say just a trivial result from expansion in eigenfunctions of the linear time invariant operator. Where a key point might be the following. X of t, that's our signal in the time domain, and basically its sort of projection onto different eigenfunctions, capital X of omega, those are just different ways, are just different representations or expansions in different bases of some abstract signal x. So that's sort of begging us to start thinking about how do we talk about this in the infinite dimensional setting. And the first thing that we may want to do is start thinking, how do we replace all these vectors with something new? And what we're going to do is we're going to replace those with signals, so that now we'll have sets of signals instead of sets of vectors. And we'll be able to get, instead of vector spaces, we'll do signal spaces. And we'll be able to introduce norms, a sense of distance between signals, just like we had norms with our vector spaces. What else did we do then after we had a norm? Then we looked at inner products, didn't we? And we said, oh, maybe we need this sense of angle, or how do these different signals align? How close is one signal to another? And we can start playing in terms of signal spaces like we've been playing in vector spaces. So that's where we want to go, which means let's now talk about this idea of signal spaces. And to begin with, let's just sort of get clear what some possibilities might be. By that I mean, let's look at some sets of signals. Just like we had many different vectors, we had polynomials, but we had the normal Rn and Cn, etc. So let's now first recall that in the finite dimensional case, we started with a set of vectors. Here, what we want to start with is a set of signals. So let's look at some typical sets of signals, and these are actually in the book by Franks, some of these. Some examples. For example, sets of sinusoids, which maybe we will call capital S sub s. That might be then this set of signals x such that x of t is equal to the real part of this complex exponential e to the alpha plus j 2 pi ft plus theta. Where t can live between minus infinity and plus infinity, and f, that's our real function. Theta is, let's say, a real angle, and alpha is some value that gets us an amplitude. So that those are all belonging to the real numbers, f, alpha, and theta. That's now a set of sinusoids, depending on the choice of f, alpha, and theta. Or maybe we think of an alternative way of parameterizing that set of sinusoids. Maybe we say it's the set of x such that the second partial of x with respect to time plus, let's say, some parameter, we'll just say lambda squared x of t is equal to 0. Again, for t between minus infinity and infinity, and lambda some real number. And now x of t is going to be producing these sinusoids if those signals satisfy this governing relationship for two times, differentiate it twice, and add it to some scaled version of the original signal x, and that will produce sinusoids. Another signal, maybe we consider energy limited signals, or in earlier classes we may have just called those energy signals. They had a bounded energy, so that we might say, oh, that's S sub E of, let's say, capital K. That's now the set of signals x, such that if we integrated x squared over all time, it would actually be a bounded integral. So, uh-oh. Shouldn't be clicking so many different places. Please come back. Okay. It's looking better, but now you can see that we do have they think it's funny in the other room. Maybe you won't hear that in the audio, but you can rest assured that someone's actually laughing in the other room. Uh-oh. And it is getting to be a little bit comical, maybe. So that now what I have are these different, wow. Guess maybe I need to Now I'm losing my patience. Let's see what we can do, and if not, then I may just do the rest on the board and talk my way through it and then fill in after the fact with the tablet. So here what I want to do is talk about different signals. We might have signals, let's say we had the first case, which were sinusoids. The second case was then this energy limited or energy signals. Now we might have duration limited signals, which are S sub D, which simply means, and maybe we have those limited by some large interval or short interval of time, capital T. We now say that that's the set of signals x, such that x of t is equal to 0 for all values of time t bigger than this interval t. So it's now saying that the signals are 0 outside minus t to t. That's duration limited. And you could see that those are sort of stacking up on each other in terms of if you looked at S sub D of, or if your signal x was actually a duration limited waveform, let's say by t sub 1, that would then imply that x belongs to S sub D of t sub 2, if what relationship exists between capital T sub 2 and T sub 1. So now if T sub 1 is less than T sub 2, this inclusion will be true, right? Or if T sub 2 is bigger than T sub 1. Running out of board space. What else do we have? We also have band limited. We had duration limited, that's in the time domain. We could have band limited. Which now says that we might have this S sub B. Let's say this is now a function of omega, are the set of signals x such that x of f equaling this integral from minus infinity to infinity of x of t e to the minus j 2 pi ft dt is equal to 0 for all frequencies, let's say bigger than some omega. And that's now band limited. And we could even now use this concept of union and intersection of sets to produce more interesting sets with combinations. So we can now apply these set operations of, let's say, union and intersection to these signal sets. For example, what if I took the time or the duration limited, those signals that are only valid over a finite interval of time, and what if I intersected that with the bandwidth limited signals that are now only containing signals or waveforms that only contain certain frequencies or a finite limit on our frequencies? What do you know is true about that intersection? Is there anything special about a duration limited and a band limited signal in terms of their intersection? Can you have a time limited signal with finite bandwidth? Or you might think of, what if I took the Fourier transform to find the frequency content of a duration limited or a time limited waveform? What kind of a transform do you get? Meaning now if you had a duration limited waveform, maybe that's this x of t, where this might be cap t over 2 and this is minus t over 2 or something, a pulse. What do you know about its frequency content? Do you remember what the Fourier transform of that is? Is that a sink? I see people starting to do this. And what do those tails of the sink do? Do they stop? No, they just keep going and going, don't they? So this intersection of a time duration limited and a bandwidth limited signal is actually just the only signal that you're going to get is the zero signal. So this is now the set of x such that x of t is equal to 0 for all time. And that's the only signal that's both band limited and time limited. And I think we will stop at that point, but that now gives us, now that we have this set of signals, we can now start to partition those sets of signals, like I said at the beginning of class, into maybe a class of signals that correspond to a 1 and another class that corresponds to 0. Or maybe we have a larger partitioning that we want to do in our set of signals. But now that we have these signals, we can start to build up signal spaces that contain norms or distances and inner products. And that's where we'll start and finish on Wednesday.